Okay. Now, yeah, let's get started. So here's the background. G is an ambient abelian group, and A is any subset of G. We define a subset A plus A to be the set of contains all those elements of the form A1 plus A2, where A1, A2 they all belongs to A. And we also define a set A is said to be sum free if its subset, if the union of its subset with itself is an empty set. So in other words, for any triples x, y, z in A, we will get x plus y is not equal to z. Okay, here's a little remark. Subset is not preserved under translation. This is because for, this actually means if a set A is sum free, it does not necessarily imply that A plus B is also sum free, where B is any element in G. Well, this is simply because x plus y not equal to z does not imply x plus b plus y plus b not equal to z plus b, because you get an extra b on the left hand side. Okay. Yeah. And a natural question is, given a structure S, what's the size of the largest sum-free subset of S? So here the structure S can be understood as the group G itself, or any subgroup of G, or even any subset of G. Okay, let's take a look at the first question. What's the size of the largest sum-free subset of a group G? Well, when G is a finite abelian group, the problem was studied since the 60s and finally resolved by Green and Rusha in 2005. And here's another example. So we define breaking n here to be the first n natural numbers. So we would like to ask, what's the size of the largest subset of the first n natural numbers? Well, the fact is that the size of largest subset of breaking n is roughly n over 2. And there are at least 2 examples. The first one is that we take all those odd integers, and because we know an odd number at an odd number is an even number. So clearly the set of odd integers would be the sum free. And the second example is that we take the half interval. Basically, we take out all those big numbers in the first n natural numbers. So any 2 elements in this interval, their sum is bigger than n. So that implies that this half interval is sum free. And the proof of this fact is actually not too hard, because we can just take A, be a subset of breaking n, and also sum free. And suppose there's a natural order here, A less than A2 less so on and so forth to AM. Then if we take a look at this 2m-1 elements, well, first, they are distinct because A is a sum-free set. And second, these 2m-1 elements, they all belong to the set breaking n. So this simply implies 2m-1 is less equal than n, which is what we want. Okay, yeah, here I'm actually like to give one more example, which is an geometric series. So we take X to be the geometric series with base 2. So it's 1, 2, 2 square, 2 cube, so on and so forth, to 2 to the n-1. Well, the claim is that this set is actually sum free. So the set itself is actually a sum free set. Yeah, so what I'm going to say is geometric set, they are automatically sum free because the elements grows too fast somehow. Okay, so here I basically give you some special sets, special subset of positive integers. So what if A is arbitrary set of size n? What's the size of largest sum-free subset of A? And this is a question asked by Erdős in the 1965. And let me introduce one more notation here. So we define this quantity M21n as the right-hand side where the increment is taking over, the increment here is taking over all those arbitrary sets of natural number of size n. And the maximum here are taking all those sum-free subset of A. So Erdős question basically asks, what is this quantity to M21n? Okay. To make a precise statement of the quantity M21n is actually the sum-free conjecture. So the statement goes like this: there exists a constant C and an unbounded function omega, such that for any small epsilon, we have an upper bound, which is C plus epsilon times n, and a lower bound, which is C times n plus some unbounded function omega. Okay, so morally, we can think of M21n. This is roughly equals to the main term plus some everything. Yeah, everything goes like this. And for the lower bound, I think there are three results. The first is given by Erdős in 1965, who proved that the lower bound is bigger than n/3. And this result was later improved by Allen and Kleckman in 1990s to n+1/3. And in 1997, Progresson improved this result to n+2/3. And this is by far the best result. And for the upper bound, I think there are many results. I'm not sure I'm giving a complete list here, as you can see, there are many results, and it was until 2013, Eberhard, Green, and Manus, they solved the upper bound conjecture for the upper bound case for the sum-free conjecture. So basically, the upper bound is is at most 1/3 plus some Everton times n. Okay. Now I'm going to give you or show you the probabilistic argument given by Erdős. What Erdős proof is this lower bound, and the proof is simple but really elegant, I think. So we take omega to be this interval 1/3, 2/3, and clearly omega is sum-free because 1/3 plus 1/3 is 2/3, which is small. Sorry, which is big enough, and 2/3 plus 2/3 is 1 plus 1/3, which is just 1/3. It's small enough, so the set is sum-free. And given any arbitrary set A, we define the set AX as the following. Well, let's say as the following. Then the claim is that the set AX is sum-free. Well, this is because I suppose on the contrary, there are some elements n1, n2, n3. They all belongs to AX, but the sum of the first two number is the third one. Then this would imply n1x plus n2x equals to n3x. Oops. Yeah, n3x. Well, all these three elements lies in AX. Sorry, all these three elements lies in omega, and this would contradict to the fact that omega is sum-free. Okay. Now for the this means that the size of the largest sum-free subset of A is at least AX, where we can take S to be an arbitrary point on the torus, which is our quotient Z. We can calculate the expectation of AX in terms of X, which is exactly n/3. So by Petri-Hawley principle, there has to be a point x such that ax, the size of ax has a lower bound n over 3, and this basically proves the other result. Yeah. And yeah, if you look at the set omega here, it's a set on the torus of Lebesgue measure 1/3. So you might ask, can we find another measurable set omega which is sum free, but has measure greater than 1/3, strictly greater than 1/3? Well, the answer is no. This is because of the Kneser's inequality. So Kneser's inequality tells us if you have two sets A, B, then the measure of its sum set is greater than the sum of their measure, which is mu A plus mu B. And as a result, if omega is a sum free, it means that the sum set intersect itself is an empty set. So the measure of the sum set plus the measure of itself should be less equal than the measure of the whole torus, which is 1. And this term has a lower bound 2 times the measure of omega. So this gives the measure of omega has to be less than 1/3. Okay. By modifying earlier arguments a little bit, Allen and Kahneman are applying the improvement to n+1/3. And this proof is not quite hard because we just need to observe that there exists a point x on the torus such that this quantity would just be the size of ax minus n over 3. So this quantity is strictly greater than 0. It implies that the size of ax is strictly greater than n over 3. And because ax is a set of integers, it will immediately implies that ax is greater or equal than n+1 over 3. Yeah. So this gives the proof. And for the choice of x, we can consider x as this point of the form m over p, where p is a large prime. Okay. For the latest result, Bourgain used Fourier analysis to prove the current world record n+2 over 3. And yeah, this proof is quite technical actually. Okay, now we are in position to introduce the KL sum free set. So a set A is said to be KL sum free if for any k numbers x1 to xk, any L numbers y1 to yl belongs to A, such that the sum of xi is not equal to the sum of yj. Yeah. And now we similarly introduce this quantity mkln, where the maximum here are taking over all those KL sum free subset inside A. Okay. So using this notation, sum free is just 2-1 sum free. Yeah. So somehow when I mention 2-1 sum free, it is equivalent to the original sum free. And also 2-1 sum free and 1-2 sum free, they are equivalent because these two number KL, they are kind of symmetry. Okay. And we can similarly make a KL sum free conjecture. So there exists a constant, absolute constant C, depends on K and L, and a bounded function omega, such that we have a upper bound that goes like this and lower bound goes like this. And for the KL sum free problem, Bourgain in the same paper shows that the M31n has a lower bound n over 4 plus some unbounded function. So basically, program proved the 3-1 sum-free conjecture, the lower bound cases. I think Eberhard in 2015 proved that CK1, the constant for K1 sum-free problem, is just 1 over K plus Shukun. So in collaboration with Jing, we first showed that the constant CKL for the KL sum-free problem is just 1 over K plus L. To be specific, we show that the upper bound of MKLN is the desired upper bound, but the lower bound here is not the optimal one because we don't know whether is it true when the lower bound has some extra error term omega n and unbounded function omega n. This is something we don't know for general KL, but we are able to prove this case for some, prove this conjecture for some special case. Say K equals to 3L or K equals to 5L or K equals to 2L when L is an even number. Yeah, in these cases, we prove the lower bound cases. Okay, so this is basically our result. And yeah, now I'm going to give you a sketch of proof for the upper bound case. So we first define upper density of on a set A to be the following complicated expression. And follow the idea from Wu and Shang, we are able to show that any set A, if A is KL sum-free, then the upper density of A is bounded by 1 over K plus L. So this is an auxiliary result we would like to use. And on the other hand, we introduced the bonus sequence. So a bonus sequence is basically a sequence of set phi n, such that for this sequence, I will say this sequence for every integer A, the different set here, well, the density of this different set is pretty small, and it actually goes to 0 as m goes to infinity. Yeah, and we are going to show that the bonus sequence cannot have a large KL sum-free subset, and yeah, and followed by an idea from Eberhard, we are able to show that for a bonus sequence, and suppose that there are infinitely many m, such that the bonus set phi m has a KL sum-free subset of density delta, then there exists a KL sum-free set A, such that the upper density of A is greater or equal than delta. So combined with the result I stated before, we can see that this delta has to be less equal 1 over K plus L. So this basically gives the upper bound construction for the KL sum-free problem. Okay. Now let's go to the lower bound cases. So let me first recall the original sum-free conjecture. So it wants us to prove whether this quantity has a lower bound n over 3 plus some unbounded function omega. So let me refer this version as the combinatorial version. And if we define omega as we did before, then we have an analytic version of the sum-free problem, which is just the supreme of this quantity. It would just be ax minus n over 3 is greater than some unbounded function omega. So as I showed to you before, the analytic version will imply the combinatorial version immediately. And actually, people do not usually attack the original sum-free conjecture or the combinatorial version directly. They just prove some result for the analytic version, and it would then implies the same result for the combinatorial version. And for the analytic version, we actually can prove the following lemma. So assume that the analytic version of the sum-free conjecture is true. Then for any k, we can find a set omega k 2k with measure 1/3k, such that the left-hand side here, which can be understood as some set ax minus 1/3k. So here the set ax depends on the choice. So it's another set, but can similarly define as in the sum-free conjecture. So this quantity is bounded below by some unbounded function omega n over k. So this lemma basically said sum-free or 1-2 sum-free or 1-2 sum-free implies k 2k sum-free. And the proof is not hard. Actually, here is a scheduled proof for the case 1-2 sum-free implies 2-4 sum-free. So we define omega as usual, and we consider map chi, who map x to 2x. Then the pullback of this map is actually the union of two intervals, omega 1 and omega 2. And both omega 1 and omega 2, they are 2-4 sum-free. So by pigeonholing, this desired estimate hold for either omega 1 or omega 2, which would imply the analytic version of the 2-4 sum-free problem. So yeah, this basically is the proof. And because of this lemma, we kind of think that 2-4 sum-free is the, well, most interesting cases among all those KL sum-free conjecture other than the original sum-free problem. Although we cannot prove the sum-free conjecture, we can prove the 2-4 sum-free conjecture for the lower bound directly. And this is what we did. We proved that M2 has a lower bound n over 6 plus some unbounded term. And in the rest of the talk, I quickly will show you the proof. Okay. So we introduced two sets, omega 1 and omega 2. And just to remind you, both these two sets, they are 2-4 sum-free. And we define a balanced function ft as this. And we are going to prove that the supreme of these two quantity has a lower bound log n over log n. So suppose this estimate is true, say for f1, then we also notice that we also have the integral of this function on the torus, it is 0. So this would imply the integral of its positive part has a lower bound log n over log n. And this suffices to prove the 2-4 sum-free conjecture. Yeah. And in order to prove this desired estimate, we define f to be the sum of f1 and f2, and f star be f1 minus f2. And we only need to prove the same estimates for f1 and f2 replaced by f and f star. Okay, this is just triangle equality, I guess. Okay, let's first take a look at f star. So by Fourier inversion, we can write f star into this Fourier series of sum of n greater than 1 phi n over n times sine 2 pi nx. So here phi n is a periodic function, but not a multiplicative function. And because of this, it will cause a little difficulty in our proof, simply because if you want to sieve out all those n in this summation with small prime factors, but then the error term would kind of blow up. And on the other hand, if we want to keep the error term small, but then we might face too many main terms. So there were a balance between the error term and the main term. And in order to get around this difficulty, we kind of carefully construct a sieve C, so that the left-hand side, so that using this sieve, the left-hand side, which is a combination of F star, can be written as the right-hand side, which is sum of main term plus an error term. And one more remark here is that the sieve C is also not multiplicative, because of the bad behavior of the Fourier expansion of F star. Okay. And also here, the set X is a set of square-free integers generated by small primes. And the set Y here is a set of integers that only contains big prime factors. And epsilon is a function whose absolute value is always 1. Okay. Now, similarly for the function f, we can have the similar estimates using a different sieve eta here. Well, the sieve eta here is rather simple because at least it is multiplicative. Okay, so we end up with the combination of f on the left-hand side equals to the right-hand side, which is also a sum of main term plus a sum of the error term. Okay. Putting those two estimates together, we can have the combination of the f star plus the combination of f is roughly equal to the sum of main term plus the sum of error term. And if the difference set here, so this is the difference set, if the difference set is large enough, then the L1 norm of the above function is good enough to give us the 2-for-some-free conjecture. And it indeed can be estimated by applying a variant of McGehee-Picknell-Smith theorem. So here's the variant we would like to use. Let B be a set of integers of size capital M, and let Q be a big number, and we define Y as usual to be the set of natural numbers only contains big prime factors. Then the L1 norm of the sum of main term and the error term has a lower bound log M. And what McGehee-Picknell-Smith, what they proved is that the main term L1 norm for the main term has a lower bound log M. And this is also known as the weak Littlewood conjecture, I guess. So this weak Littlewood conjecture was proved by McGehee-Picknell-Smith and Yifan Jing independently. And if you are interested, there's also a strong Littlewood conjecture, which is still open. Okay. So this is the estimate we need, and our argument follows from the idea of McGehee-Picknell-Smith, as well as some ideas from Bourgain. Using this estimate, when the difference set is large enough, say its size is roughly n to the some small power of n to the some small positive power, then the combination of f star and plus the combination of f, the L1 norm has a lower bound log n. So we also let's take a look at the coefficient here. So this two coefficient, they actually has an upper bound log n by Merton's estimate. So if we divided this to coefficient to the right-hand side using the triangle inequalities, we can conclude what we need, which is the supreme of f star, and f has a lower bound log n over log n. So this would prove the 2-4 sum free conjecture for the lower bound cases. If we're given this condition, so the size of the different set is pretty large. Well, this argument would fail if the different set is pretty small. And this is simply the reason why we did not include this result in our first 2-4 sum free write-up. And at that time, we don't know how to get around this difficulty. And it's after months later when we were doing some study or doing some reading on the Gauss norm or some approximate polynomial stuff. And we kind of ask ourselves, when the different set is small, is there any extra structure we can say on the set A? Well, indeed, there is. First, I want to point out is that when the different set, when this different set is small, it actually can be think of as close to a Fourier set, because in the Fourier sequence, we require the density of the different set is fairly small, or actually it goes to infinity. It goes to 0, Sm goes to infinity. And we also know the Fourier sequence is an upper bound construction for the sum free conjecture. So here is a relative question. If A is close to a Fourier set, does A necessarily has a large sum free subset? Okay. Now let me introduce one more notation. So for positive integer A, we partition the natural numbers using the geometric series of A, and we said the set A is M Lacunary if A cannot be covered by less than M sets in this partition. So here are two examples. An arithmetic progression of size n is log n Lacunary, and a geometric series of size n is n Lacunary. So I would say here is that the Lacunary, the terms here, will measure whether a series is close to a geometric series or not. Okay. Also, there's another key observation. Any set f of size n is at least n over the different set Lacunary. Somehow this is because we can partition the set f into the unions of A chain. So we would like to do this kind of partition. So what is a chain? An A chain will start with a number A1, then it goes like A1 times A, then it goes like, and the third term would be A1 times A squared, and so on and so forth. So it would be, can be think of as a translated geometric series. Also, the set F may contain some other A chains, which start with A2 and goes like A2 times A and A2 times A squared. And eventually, there's a chain start with AM and goes like AM times A, AM times A squared, so on and so forth. Without loss of generality, let's assume the first geometric series is the longest one and have size m tilde. So the size of F has an upper bound m times m tilde, which gives the m tilde has a lower bound F over m. We also notice that n is, well, 2m is just equals to F, the different set, the size of the different set. And because F contains a geometric series of m terms here, and a geometric series itself is Lacunary somehow. So this would prove the observation. Okay. And we make one more definition by defining a set A is geometric if A is at least log n to some big power Lacunary. And what we are able to show that is geometric sets satisfy the lower bound cases for the sum-free conjecture. And this would in turn prove the two-fold sum-free conjecture when the different set is small. Actually, this would prove the two-fold sum-free conjecture for geometric sets. And because when the different set is small, by this observation here, the set A would automatically be a geometric set. So yeah, this would prove the other part of the two-fold sum-free conjecture, which is the different set is small. Okay. Now I'm going to give the proof of the sum-free problems for the geometric set. So by Fourier inversion, we have the left-hand side is equal, which is just AX minus n over 3 again, is equal to Fourier expansion. And here Chi is a multiplicative character mode 3, which also is a multiplicative function. Yeah, and we define F as the balance function. And somehow we can write, so somehow we can have this end up with this expansion. And we take a big prime and define the set X as the set of square free integers generated by those small primes, and define Y be those integers are either is 1 or only contains big prime factors. Now we use this function mu times chi as a sieve. So here mu is the Mobius function. So that by inclusion-exclusion principle, or by the sieve, the left-hand side, which is combination of F, is roughly the right-hand side. And the right-hand side here can be interpreted as the sum of a main term, which is the case n equals to 1, plus the sum of the error term, which is the case, which is the case when n is greater than 1. Okay, and by the triangle inequality again, the combination of F, the L1 norm, has a lower bound, which is the L1 norm of the main term minus the L1 norm of the error term. And the error term can be estimated by Plancherel and Cauchy-Schwarz, and it is of size of 1 and hence can be discarded safely. And when the set A is geometric, the main term here actually has a lower bound of log n. So, and this result can be deduced by the classic Littlewood-Paley theory. Because of that, we have the left-hand side, the L1 norm of the left-hand side has a lower bound log n. And by Merton's estimate again, divided this coefficient to the right-hand side and end up with the L1 norm of F has a lower bound log n over log n. And this is what we need to prove the sum-free problems, the lower bound cases. And yeah, by the triangle inequality, we will conclude our results. Okay. Here are some future directions. The first one, of course, is the sum-free conjecture. We cannot prove this conjecture. What we can do is we only prove it for a very special case, which we call it the geometric sets. And the second interesting problem may be explore the relation between sum-free and the two-fold sum-free combinatoric version. So what we are able to show that is the analytic version. So analytic version sum-free implies 2 for sum free. We don't know whether the original sum free problem would imply the 2 for sum free problem. This might be an interesting topic. And also, it would be interesting to know whether the KL sum free conjecture would hold for different pairs KL. Here we only prove K equals to 5L, K equals to 3L, and some special cases for when K equals to 2L. And finally, you might be interested to prove the upper bound cases for the restricted KL sum free sets. So in KL sum free set, we have K number x1 to xk, y1 to yl. In a restricted problem, we make a further requirement that these numbers they are mutually how do I say that? They are not equal basically. And the same for y. So we believe the same upper bound for KL sum free problem is the upper bound for the restricted problem. But we haven't given a proof yet. But yeah, but we believe it will be true for the restricted problem. Yeah, and that's it. Thank you.